Okay, so it is the 27th International Conference Electronics. This year it is being held virtually, and we hope to see all of you next year. Well, we received 20 papers from 24 countries, and it's usually it is a average number of the countries which we receive. Sometimes it could be a bit higher, sometimes goes down, but average around 25 countries every year submit papers to the conference. And after the strict review process, some countries left, and 18 countries, 18 participants from 18 countries registered to the conference, and papers were accepted to the conference. Well, the review process was enough strict. 55% of the papers were rejected, and as you see, the trend which started, we count from 2012, it is around the average as well. If we count all the year from 2012, so the average rejection ratio is 63%. So now we had 55, so more or less very similar. The reason is very different. Reasons are very different because majority of the papers were rejected by the reviewers based on their recommendations. But what was unusual this year, that several participants decided to cancel their participation even virtually after the accepted paper notification. So usually this number is very low, but this year it was a bit higher than we had in the previous year. Also, there are a bit change in the popular topic of the year. In the past years, the most popular was electrical engineering topic. This year, the system engineering and computer technologies took the first place. And I would like to ask you to be active during the presentations, because at the end of the conference, you will get a link to vote for the best presentation. And there is an award for the best presentation from our sponsor, Siglent. It is oscilloscope. And I hope that will motivate presenters to increase the quality and to make more fruitful discussions. And the prize from the last year went to India, and there is a photo of the winner that oscilloscope arrived successfully. So I would like to thank you and wish you a fruitful conference. And I would like to invite the first keynote speaker, Jose Carrasco. So please.
Hello, good morning.
Good morning.
So I may start with the presentation, right?
Yeah.
Yeah. Okay. So my name is Jose Carrasco. I'm the CEO of an smart company based in Spain, and we manufacture electronic systems for space applications. I'm going to share my screen because I've got Okay, I believe you are seeing the first page of my presentation. So the presentation is going to deal with stability criteria on power bus architectures used in satellites in a space platform, and the relationship of this stability criteria with the EMI, which is the electromagnetic interference of the power systems connected to the main power bus of the satellite. As I've said, my name is Jose Carrasco, and you've got my email there in case you want to drop me an email to ask me something related with the presentation. The outline of the presentation is going to be this one. I will present a little bit of my company, and then the basic requirements for satellite power supplies that relate to compliance with impedance requirements and electromagnetic compatibility requirements. I'm going to deal only with the conduction, electromagnetic compatibility. The radiators are another field, or it will take me much more time than what I have today. Then I will, just to align ourselves, describe the satellite power system basics. Then I will summarize very quickly the space power standards. And then I will deal with the impulse-fitted design. Why does it matters for compatibility and electromagnetic radiation conduction requirements fulfillment. And then I will describe in a small example and end up with some conclusions. Well, as I told you, I work in a very small company that was founded 17 years ago. We have participated in 4 space missions. Just as a curiosity, we are in 1 Guinness World Record, 2009, for the biggest platform in orbit. And we have participated in more than 30 space-related projects, mainly with European companies and space agencies, like mainly for the European Space Agency. So you can see here some of our products. This month, we are delivering 1 instrument that goes to an asteroid on board of the HERE mission to measure the gravity of the asteroid. It will be deployed on board one of the CubeSats that travel to the asteroid that will land on the asteroid, and while on the free fall to the asteroid, the landing, it will measure the gravity. We are delivering this instrument this month. Another thing that we have, just to show, we are manufacturers of small space platforms, and we have all the subsystems that configure the space platform. So this is all manufactured by ourselves. Next year, we have our first flight of a demonstration mission to qualify 1 small CubeSat, a 3U CubeSat, and 1 6U CubeSat will follow. And the particular characteristic of this small platform that we have is that we provide optical communication, not just communication by radio, but also by an optical link. And that eases a lot getting the licenses to transmit data from Earth to the ground. You have here some of the examples of our technology. We produce everything in our facilities, in our working room. We assemble the CubeSat, and we also manufacture the Earth station to have the optical link and the radio link with the satellite. As I told you, we have 3 missions ahead. 1 for demonstration of technology of our CubeSats with the optical links. The second one for the small gravimeter that goes on board the Algimantas, or on board a small CubeSat and that lands on an asteroid that will travel on board of the HERE mission that is made by the European Space Agency, and then another small CubeSat launched by a university close to us that will have an experiment of particle physics. We also are able to manufacture power systems, and you have there a power supply that we've done for the European Space Agency. It is a little bit blurred on purpose, and the main features of this power supply is that it has to have a very low emissions of interferences, in particular conductive emissions of electromagnetic radiation. in differential mode and in common mode. You have there the ESA requirements for electromagnetic conductive emissions, and the purpose of this power supply is to have less than 20 dBs, the usual standard for electromagnetic compatibility, for electromagnetic conductive emissions. And this is something that is being demanded by the space industry because the new science experiments and new optical link for communication require very have sensors that require very high signal to noise ratio, and the production of electromagnetic power supplies that produce a very low level of electromagnetic noise is a must for these new scientific missions and for the for application like optical communications. So just to summarize what the problem is, in a usual satellite, we have some loads connected to the satellite power bus that distributes the voltage. And in the middle, we need a power supply. The power supplies are usually switch mode power supplies because we need to transfer power with a lot of efficiency. And the switching of current and voltages generates electromagnetic noise. And we remove this electromagnetic noise that is generated inside the power supply using filters. Of course, there is a filter at the output of the power supply that connects it to the payload or the platform component. And we have to put a filter at the input of the power supply to connect it to the satellite bus to reduce the noise that we deliver to the bus in order not to enter in conflict with another payloads and another power supplies. In principle, I'm sticking here to the requirements of the European Space Agency, and these are the requirements for the differential mode electronic noise emission. So if we measure the current in both the supply and the return lines, we are required to have less than these limits for the difference of currents that go in and then go out, and at low frequencies, this accounts for 10 milliamp, less than 10 milliamps of difference of these two currents if the power supply has 1 amp input. If it has more than this 1 amp, the limits change. Of course, we may find differential mode electromagnetic emission and common mode electromagnetic emission. If we measure the current at both ends, the supply and the return line at the same time, we may measure a difference as well. And there is a maximum limit given by this requirement here that we may account for this difference to have a power supply that we may deliver into a satellite platform. This is again for common mode. There is no change in the limit depending on the power of the power supply, and it's always a maximum of 10 milliamps difference between this common measurement and the common ground of the satellite that we may measure. So just to align ourselves, okay, so what happens if we are trying to comply this electromagnetic emission by putting an input filter? That is what we need. The thing is that we have an input impedance to the power supply, and if we put that we have to connect to the satellite bus, and if we put an input filter in between, the end result of this is that the input impedance of the power supply is decreased, and this decrease depending the frequency that we have, decreases more or less. And these are some examples of the decrease of the input impedance of the power supply when we put a filter. For usual power supply, the input impedance is more or less constant, so we will have in frequency a line just horizontal. But if we put an input filter, we may get the orange line is the input impedance of the power supply, a decrease depending on the input filter. The blue line is the output impedance of the satellite bus. And we may have these three scenarios. We may have an input impedance that decreases and doesn't touch the output impedance of the satellite bus. We may have an input impedance plus including the filter that nearly touches the output impedance of the power supply, or an input impedance that just crosses the output impedance of the satellite bus. If in any of these scenarios, instabilities may occur. If the input impedance of the power supply pass filter is well above the output impedance of the satellite bus, we have no trouble. But if we enter into any of these two scenarios in the middle or in the right, we nearly touch or we cross the two impedances, we may have instability problems. And the bigger we want the input filter to reduce the electromagnetic emission, the more problematic may be connecting a power supply with an input filter to a satellite bus. So this is the main problem that we encounter when connecting things to a satellite power bus. And just to align ourselves, I just would like to remind what's a satellite. When a satellite, we have a platform and some payloads. The platform is made out of those subsystems that make the satellite fly. So it has the power system, the distribution, the onboard computer, the attitude control system, the thrust, the radios. So a platform could fly on its own with no payloads, but it will have no purpose. And the payloads are the things that make the satellite, that define the purpose of the satellite. So payloads provide the telecom applications or the science applications of the observation of deep space. And any of the power supplies that configure that supply power to the telecom radios of the science experiments of the deep space cameras or experiments have a power supply that needs to be connected to the satellite power distribution bus and then needs to comply with these impedance requirements and electromagnetic compatibility requirements. So mainly, and just to continue the remembering, in satellite power buses, we have unregulated buses where we have the battery connected directly to the bus. Of course, there are some protections in the middle, but we are, from the point of view of the loads, either the platform loads or the payload loads, we are seeing the battery, just the impedance of the battery. Or we have regulated buses where we have either the solar array regulator or the battery charge regulator or battery discharge regulator are regulating the voltage of the bus. So the bus impedance that we see is either the output impedance of one of these three systems. So this line here is the line that goes to the satellite bus, to the power distribution. Of course, we have some protections in the middle. And from this satellite bus, we connect the power supplies that give power to the loads, to the platform loads, or the payload loads, and in between we need this input filter to remove the electromagnetic noise. And for defining the way to connect these power systems to the power bus, we have three power standards. One is defined by the American Institute of Aeronautics and Astronautics. It was defined in 2007. You might find it there. And it defines how we connect or how we define electrical power system for unmanned spacecraft. The other one is the aerospace standard that was published by the SAE Aerospace. And there was a first edition in 2007, and there is a revision in 2018. So this one is the most, maybe the most modern and the most updated. And it's most updated than the one from the American Institute of Aeronautics. If you want to obtain either of these two, you have to pay to these organizations. There is a third one that is the one we in our company used, which is the one issued by the European Coordinations for Space Standardization. That is an organization that depends on the European Space Agency and is the standard that the European Space Agency follows. There is an issue from 2018, and there has been several reissues of that. The first edition was published in 1992. so nearly 30 years ago. And I say this because it's going to be important in what follows. So if we analyze these three, of course, you can take any of these to define your electrical power system of your satellite. If you take the first one, the one by the American Institute of Aeronautics and Astronautics, you find that you may have defined your power system using 4 different bus voltages from 28 to 100 volts, depending on the power you want to distribute. And the only requirement that you may find there is that the phase margin of your power supplies should be at least 30 degrees with a phase margin of at least 6 dBs. So this is, for me, is a quite weak requirement, because if you remind for your basic control theory course, the phase margin of 30 degrees in a power supply means that the damping coefficient is going to be quite close to 0.3. And if you make a change of this in this power supply, either of voltage or current consumption, you are going to have with a damping coefficient of 0.3, you're going to have a quite oscillating time response, because there is a quite big resonance in your frequency response. So it's just quite weak stability criteria, but this is what this power standard define. And then the second definition that they do is what happens if we connect some power supply to the satellite bus. If we connect some power supply to the satellite bus, the power supply input impedance is represented by ZL. The satellite bus, by the output impedance of the satellite bus is ZS. And you may find one of these 2 scenarios. First one is the 2 impedances are one above the other, with a big or small difference between both, or the 2 impedances intersect. If this standard, what it defines is that there's a separation of 6 dBs between the input impedance and output impedance of the things we are connecting. We have no problem of stability or oscillation. And if we have some intersection or touching between the impedance, we need to make some extra work or some extra study on what is happening there. And the extra work of extra study, that is what's related to the American Institute of Aeronautics Astronautics. I'm going there to the aerospace standard of the SAE. The first edition, I would like to remark something, because it will appear later, is that this standard defines the several voltages depending on the powers you are dealing with, and they define an input impedance minimum curve that the systems that we are connecting to the power bus should have. So if we design a power supply, we put an input filter, our input impedance of the power supply shouldn't go below a certain mask. Okay? The certain mask is defined in units per ohm of the input impedance of the power supply. I'm not going to enter in what this means, but just to draw your attention on that, if we have an input impedance curve here, we cannot go below. Whatever happens, we cannot go below a certain curve. This is what was defined in the aerospace standard of 2007. And the funny thing is that in the aerospace standard of 2018 revision, this requirement of the minimum input impedance of the power supply is connected to the satellite power bus was removed. And if you look at the record of changes, they say that they remove this requirement for the minimum input impedance of the power supply, because there are better tests to test for stability of the power system. And the rationale for this removing is just because, okay, they say that we don't need it, and they say that the impedance curve is a requirement that may be substituted by the studying of the Nyquist criteria on the connection of the power system with the satellite power bus. So, and what this means is that if we connect a power supply that is modeled with with an impedance that is the input impedance of the power supply that we connect to the bus, we have the satellite bus voltage with an output impedance. If we calculate what is the voltage here in the middle, and this is this one, the equation that you have is similar to the equation of a closed loop system where this block has a gain of 1 and this block has a gain of CO divided by C in, so the ratio of the two impedances. So it looks like as if the voltage I see here is a voltage defined by an open loop function whose open loop transfer function is the ratio between the output impedance of the system and connected to the bus. The output impedance of the power bus and the input impedance of the system I'm connected to the bus. And I can study the stability of this by plotting a Nyquist plot. And if we avoid this zone here, we are in a stable area, and we provide this 30 degrees phase margin, 0.3%, 0.3 damping coefficient, and we are in a stable area for our connection of power system and satellite buses. So we don't need anything else. Okay, then we go to the European standard, which is the one that we use, and we find that is the most strict standard we may encounter. It defines 3 different voltages for the power buses: 24 volts, 50 volts, and 100 volts. And the rationale for this, for defining these 3 voltages, is that one of the requirements of the voltage of the power bus is that it should always be regulated to 0.5%. And if we make a 50% load change, we shouldn't see in the power bus a voltage change bigger than 1%. If we put this into some equations, we end up requiring that this impacts on the building of the output capacitance of the power bus. And if we don't have a huge output capacitance, we have to limit ourselves in an output impedance of the power bus to a value bigger than 10 milliohms, and to have a power bus with a reasonable output capacitance, we have to limit this. We have to make the output impedance of the bus bigger than 10 milliohms. If we increase the power consumption of the power capability to deliver of the power bus, we have to increase the power by this number, the voltage by this number, to keep the output impedance to a reasonable value, to keep the output impedance, the output capacitance of the bus into a reasonable value. So, and what is curious about this power standard is that it keeps an output impedance curve for the satellite bus. So it's this one. It depends on the power we are delivering. It was introduced in 1992, so in the first edition of this power standard, and it has not been removed. So we should expect that the output impedance of the power bus is below this curve, and the value of this plateau depends on the power being delivered. So that's what I draw the attention before on your on this SAE standard, because it introduced something similar to this and it's removed in the latest edition. We still have it in the European Space Agency standards, but the European Space Agency standards still imposes that we should do some stability studies based on the Nyquist plot when we connect power supplies to the satellite power bus. So what has all of this to do when we design a power supply? So we have a power converter, we have a satellite power bus. The power converter more or less have a constant impedance at low frequency. At high frequency, it shows some inductance behavior, but at low frequency we may approximately like that. It's a negative impedance, so this means that the phase of the impedance of the power converter starts is -108, and we put an input filter in between. So, and if we put an input filter in between, okay, we know that the input impedance of this connection of the power converter and the input filter should fit into some requirements. You have some values for several voltage of power buses and the output impedance of the power bus that results. For instance, for a 28 volts power satellite with 750 watts capability, the mask of the standard defines an input impedance, a bus impedance at the plateau of 21 milliohms. And if we do some maths, we don't get into trouble if our input, the input impedance of our power converter that we put here is over 2.1 ohms, because it's quite separate from this impedance of the satellite power bus. And if we made a change of 375 watts, which is half the power capability of the satellite power bus, we have this 1% change in the bus voltage. So these are some examples, and you may see here why when we reach 1500 watts of boost power, we have an input impedance, a satellite bus output impedance of 10 milliohms. And if we don't want to keep doing the output capacitance of the power bus bigger and bigger, we have to increase the bus voltage to still increase the bus impedance a little bit. So the output capacitance is not huge. So, okay, it's an example. So what is the result of all this? Okay, imagine that we have a satellite power bus. We have a mask for the maximum values of the satellite power bus. We are going to have this bus impedance, this curve here for the bus impedance of the satellite power bus. We have an input impedance for the power supply that is more or less a horizontal line defined by this value that goes up at high frequencies because of inductive nature of the power supply. And if we put a filter in between, the effect of this is going to be to get the input impedance of the power supply down, and to maybe get into problems because this input impedance may collide with the output impedance of the power bus. This plateau here depends on this damping resistor for the input filter, and where this drop starts and where this goes up depends on the values that we design for the inductance and the capacitance of the filter itself. So in the end, we need to put this filter to remove the noise generated for the power supply. We have to take care. The more noise we want to eliminate, the bigger we have to design this filter. And if the bigger is this filter, the bigger is going to be this drop, and the more we are going to study the design to avoid problems of crossing the input impedance of our power supply with the output impedance of the power bus to avoid stability problems. So here we have two examples of input filter design. We may purchase an input filter, maybe from Crane Aerospace, that supplies already off-the-shelf input filters that has responses like this. So you may see the capability of removing the noise. This goes to the power supply, this goes to the satellite bus, and this is the capability of the filter to remove noise at high frequencies. Of course, I didn't mention before, but for the filtering, you need a differential mode to filter the difference of currents between the supply and the return lines, and a common mode filter to filter the difference of a current between both the supply and the common line at the same time, and the main ground of the spacecraft. So the whole filter is made with this common mode and differential mode filtering. Although I'm going only to refer to the differential mode filtering what follows. So you may purchase one, You may build one by yourselves, just purchasing inductors and capacitors and assembling everything to be able to provide more or less attenuation at big frequencies. The more attenuation you have here to remove more and more electromagnetic noise, the more trouble you are going to get into for stability issues. So in the end, you are not going to be able to test your power supply in an actual satellite, but you're going to have test bench like this one. You are going to have your power supply, the power supply you are designing, and is going to be connected to a power source that looks like the satellite bus, and in the middle to provide to your power supply of what a real power supply will see when assembling to a satellite. There is something in between, which is called line impedance stabilization networks, that makes this power supply see an approximation of what the satellite bus looks like. Of course, there is always a harness in between, some wiring, and you have a load. So this is going to be your test bed for testing a DC to DC converter that you are designing, that is here with its input filter and the output filter. The harness is just wiring. Also, it's a wire with a quite big inductance because it's usually long and it's shielded. And the listen is something like this. It's defined in the E and the Open Space Agency specification. It's in a small box. It has some inductances and capacitances inside. And it has a frequency response, an impedance frequency response like this one. It's a small and low frequencies, and it goes high at high frequencies, with more or less mimics the power system and power distribution of the satellite. So when you put all this together, you end up with a power supply like this one. I'm here simulating a very simple power supply. It's a push-pull that generates some noise. It's supplying load, and it has an input filter, it has a listen, and we are also simulating the harness of the power supply. And you do one simulation and you put everything inside. You put the noise generated by the power supply due to the switching and the proper models of this to simulate the input impedance of the power supply and the output impedance of the satellite power system. You end up with something like this. We have a satellite power system and output impedance of the satellite power systems, which is this blue line. This is for a small satellite, 780 watts, 28 volts. So the output impedance has to be below this impedance mask. We know that. If we add the harness, the connection to the power supply, this output impedance at the actual connection of the power supply is going to have an inductive behavior at high frequencies. And if we take into account the listen in between, the impedance of the listen is this one, and this is the impedance of our power supply. So in order to avoid problems, in the end, we have to see what happens with the output impedance of our power supply and the interaction of this with the listen. If we are 6 dBs above the impedance of the listen, we are in a safe area. But if we are close, or even if we touch, or even if we cross, we should make some extra studies using the Nyquist diagram. And the thing is that the more we want to filter the noise, the more we want to be compatible with this very new scientific and telecommunication applications, the more trouble we have, because this input impedance of the power supply crosses the impedance of the listen. Okay, and in the end, we have to design the filtering thing to meet one of these impedance masks. So the noise generated by your power supply should be below this, depending on the input current of the power supply. I have made a very simple simulation for 1 amp power supply, 1.5 amps power supply. And the thing is just to get if you simulate this power supply in the time domain, and you get the fast Fourier transform of everything, you may get the noise it generates. And this is the noise filter at the connector with the satellite bus. Yeah, the noise generated at the satellite power bus filtered by the common mode and differential mode filter. This is only the differential mode filtering. And you see that if we design a proper filter, we are able to be well above the listen impedance, and we are going to meet the, we are going to generate a noise that is well below the ESA impedance mask. For this particular power supply, the blue one was the ECSS, the ESA required a maximum noise level, and for the requirements of this power supply I'm showing to you, it was to be 20 dBs below the ECSS noise levels. And when with the design of the input filter that we have done, we avoid the instability issues, and we met the electromagnetic compatibility differential mode requirements. The same may be done in common mode, and something similar should be done in radiation. I don't have much more time for extending myself, so I'm going to the conclusions. And the conclusions are that the requirements by the open space ESA are the most restrictive standards in the space industry, because we have to comply with an impedance mask and some stability criteria, while providing an input filter that complies with the electromagnetic compatibility criteria. And the less noise we want to deliver to the load or to the satellite power bus, the bigger this input filter has to be, because the more we want to comply, the input filter was to decrease more the input impedance of the power supply, risking the introduction of instabilities. So in the end, this input filter has to be designed to comply with the EMC, the mask, and as well the Nyquist criteria stability. And it's always needed an iterative design to match this stability criteria and an electromagnetic compatibility criteria to provide a suitable solution that meets both requirements. So expect to redesign and redesign your input filtering several times to be able to match both. And this is very much helped by modern circuit simulators, as you've seen. So thank you very much for your attention. You have my email there. If you want to drop me an email, just feel free. Thanks.
Okay, thank you.
To be on time for questions.
Do we have any questions from the audience? Probably no, but
everything seemed to be clear.
I have one question. If you simulate and then validate it experimentally, so do you have any fails? Let's say if you simulate 100 times different schemes and then you manufacture, are results the same or differs, let's say, by 5%, by 10%?
You do a simulation like this, for instance?
Yeah.
What do you mean, with the actual measurements in the laboratory, or?
Yeah.
Yeah, well, we found that we are using the LT-SPICE simulator, not because one reason is because it's free, but it's a very nice simulator, because the results that we get from our simulation validation and what we measure at the laboratory are quite close. So if you have a proper modeling of your input filters, that means having a model of the inductors and the capacitors that implement your filter. And that means, after you purchase the part, you have to measure and characterize the inductor, characterize the series resistance and the parallel capacitance of the inductors and serial resistance of the capacitors, and the serial and the serial of the parallel capacitance, the parallel inductance of the capacitor. If you characterize all the components and you put it there and make a simulation, the results are quite close to the actual laboratory measurements. So we don't see, yeah, the other thing is that one simulation with this, with everything, and this is just a simplification, takes 1 or 2 days, the simulation. But this getting this figure takes more than 1 day in LTS Spice in our computers. But the results are quite close to the actual measurement, if the models are quite close to reality.
Okay. Okay.
Yeah.
Okay. So thank you for the presentation. And now we are going to have a technical break until the next keynote speech.
Yeah. Thank you to you, and thanks for the invitation for this conference.
Thank you. Thank you.
Yeah. Have a good day.
Bye.